Howdy, it's Mr. Russell. We'll talk about factors affecting solubility. So, it's a couple of vocabulary words you need to know about solvent, solute, and you need to know what the word dissolve actually means. So, solute and solvent we've already talked about, but the word dissolve is the process in which these molecules interact and attract each other to form a solution where only one phase is visible. So, just to review what the solute and solvent are, the solute is the minority component. It's the substance that's being dissolved, and the solvent is the dissolving medium. So this is the minority component. This is the majority component here. Now, this picture is misleading because it shows you that in the final phase that they're all equal in amounts, and that's not true. You would actually get way more solvent than you would solute in proportion. There's actually a limit to how much solute you can get, but that's called saturation, and we'll get to that later. So soluble is if the solute will dissolve in the solvent, and insoluble is if the solute does not dissolve. All right. So the solvation process, FYI, there are four processes. There are four names that dissolving goes by. It's either solvation, hydration, dissolving, or dissolution. Okay, so there's four different names. So confusing, I know. So if we have a salt cube, now remember that salt is just a cube. Now we're imagining that it's full of sodium and chlorine ions, right? And so we remember that these sodium and chlorine ions are here, and they're in this crystal lattice, like you see here in the positive and negative crystal lattice. Now these water molecules we saw were really sticky. They stuck to your finger, they stuck to a penny, they stuck to a lot of different things. They had a lot of things because they have hydrogen bonding, right? Well, they're very polar, so they are going to stick to other cations and anions as well. So it's very sticky on a molecular level, as you'll see. So it will stick to these and start pulling them off. Now I want you to note the orientation here. The hydrogens are attracting the anions, or the negative anions, and the oxygens are attracting the positive cations. Okay, so that is the way that works, and it's a really cool demonstration or animation of how solvation or hydration works. So the salt cube is surrounded by water, and then the sodium ions are end up getting pulled away by the oxygens, and the chlorine ions end up getting pulled away by the hydrogens. This dissolving rate is affected by three different factors. All right. So the rate of dissolving, or how fast it will dissolve, has three factors. That's the surface area, which is how much of the outside is showing, agitation, which is how much it's being stirred, and the temperature, or how hot it is. Okay. So the surface area, if we increase the surface area, we will increase the rate of dissolving, so it will dissolve faster. So if we basically cut up a piece, a wooden chunk, it'll dissolve faster. So this powder will dissolve faster than this cube. All right, pretty simple to understand. The reason is because there is more interaction between the solute and the solvent. All right, and so they're able to dissolve each other quicker. If we agitate it, or if we stir it, there's going to be an increased rate of dissolving as well. So it'll dissolve faster. And the reason for that is also more solute to solvent contact right here. All right. Okay. And then if we increase the temperature, we will increase the rate of dissolving, so it will dissolve faster. And the reason for that is also increase the rate of solute to solvent contact. That's because the molecules are moving faster, So they will just, by happenstance, collide more frequently. And that's the way it will work for everything. If you want to increase the rate of a reaction or the rate of anything, you will increase the temperature. All right. So why do these three things help? Come on, if you hadn't noticed already, I said it 3 times. It increases the solute to solvent contact. There's a lot of S's. So we looked at how much the rate is affected. Now let's look at how much stuff can actually fit in. All right. So if we look at in terms of pressure, now remember pressure is the number of collisions, right, of the gas molecules, right? So if we increase the pressure right here, the solubility of a gas will actually increase. So a good example is bottling Coke. We bottle these Coke bottles right here, and the reason why they store them and why they're under some pressure is so that they can hold all of that CO2 and they don't lose that CO2. You'll notice that as you open it, bubbles will appear. That's because the CO2 is now bubbling out. So that's why you have to drink a Coke right away. You can't open it and come back a day later, right? Now, a solid and a liquid, it has absolutely no effect. All right, so if you add a solid to a liquid, nothing happens. It only happens with a gas, with pressure. So this also happens when you scuba dive for scuba divers, because ask yourself, will more or less gas be dissolved in a scuba diver's bloodstream during a dive? Well, it'll be more, because there is more pressure down here. There's way more pressure. So that is actually the reason why scuba divers can't go down for that long. If they do, too much nitrogen gets dissolved in their blood, so when they come back up, the nitrogen will expand and pop. That's because of Boyle's law, right? And then they get the bends. So they have to really watch their time that they go as well. Now the temperature, let's just review. We talked about pressure. Now the other one is going to be temperature. So if we increase the temperature, the solubility of a gas will actually decrease. So that's why we actually keep our sodas cold, all right? And so that they can keep their CO2. If you notice on a hot summer day, your soda will go flat a lot quicker than, say, in the winter, all right? But it is the opposite for a solid. It will increase its solubility as we increase the temperature. So ask yourself, if the pressure is increased from 1 atmosphere to 3 atmospheres, more solid sodium chloride will be dissolved into the solution. True or false? That would be false. That's because this is a solid, and solid solutes have no effect on pressure. Pressure has no effect on solid solutes. So true or false? Increasing the temperature of a gas will decrease the solubility of a gas in a solution. That is true. Okay, so increasing yeah. All right, so I want you to ask yourself one question. Why don't oil and water mix? Is it because they don't like each other? Maybe because the relationship isn't going to work out, I guess. But basically, they don't really like each other. That's because they're made of two different, they have two different attractions, if you will. All right. So if two things do not mix, we call them immiscible right here. So the terms here I want you to know are going to be, we've learned soluble, but miscible means mixable. So if the solute does dissolve, so that would be like in terms of a liquid dissolving in a liquid. So insoluble or immiscible is if the solute does not dissolve. So immiscible is what we would use with a liquid in terms, yeah. So there's a general rule of like dissolves like. So basically a polar solvent will dissolve a polar solute, and a nonpolar solvent will dissolve a nonpolar solute. Now this is not an end-all be-all rule, and if you write like dissolves like on your AP test, they will not give you credit for it. But it is a good rule of thumb to use in like a laboratory setting. So if we have a nonpolar substance here, like hexane, and we have tetrachloromethane, CCl4, which is also nonpolar, they actually do want to mix, but they are interfered with by water. Now they're separated by their different densities. Hexane has a lower density, so it's going to be on top, and CCl4 has a higher density. Now, if we shook these up and allowed them to all mix up, and if we let it settle out, we would end up with 2 layers. That's because CCl4 and hexane would mix together, and they are miscible. All right. Now, water and vinegar will actually mix together because water is polar and vinegar is also polar. Okay, because that is a type of acid. We'll get to that in acids, bases. So, all right. So if we remember like dissolves like, we're going to have a bunch of solutes here. And remember that water is polar, and then acetone is nonpolar. Just take my word for it. So if we think about nail polish right here, nail polish is nonpolar. Well, is it going to dissolve in... it is going to be insoluble in water. That's a good thing because your nail polish would come off if every time you wash your hands. That wouldn't be great. But it is soluble in acetone. So acetone is actually the nail polish remover. Now ethanol here is polar. So it is going to, it's soluble in water, but insoluble in acetone. Now if we have naphthalene, it says that it is soluble here in acetone. So acetone is nonpolar. So naphthalene must also be nonpolar. And now urea, a compound found in urine, yes, that's where we get the name, is soluble, and it is polar, and it is also polar as well. All right, I want you all to have a great day. Complete the quizzes.